Hi, welcome to the next of our series of practical electromagnetics for engineers. Today we're going to be talking about reflection coefficients on transmission lines. Where we've gotten to now is we've approximated a lossless transmission line by a lumped element model of inductors and capacitors. We lost the resistances and the conductance when we went to the lossless line. This is the last time we're going to see this because from now on we're going to represent this transmission line essentially with a symbol that looks like this, basically two parallel lines. We've taken all the parameters and we've basically converted our inductance and capacitance into a propagation coefficient beta. We know the attenuation coefficient is 0, there's no loss. The phase velocity is also given in terms of the inductance and capacitance per unit length by that equation. And most importantly, the parameter of the line we use the most is called the impedance, Z naught. And the impedance is defined to be the voltage on the line of the waves on the line divided by the current waves on the line. And that's about or approximately equal to the square root of L over C in our lossless transmission line model. And we've basically said that we have on this line two equations. The voltage is a function of position on the line. Looks like two waves, one going in the positive direction, or that way, one going in the negative direction, or that way, and the current has a similar form. But we haven't really talked about why we need two waves. So let's take a look at this right now. Let's say we've got two transmission lines we join together at this point in space right there. Those circles just mean there's a join. There's nothing else except two wires hooked together. There's no way to add voltage or current. There's no resistor to take away voltage and current. So this is a lossless type of structure. The first transmission line has an impedance of 50 ohms. So we know that V1 over I1 is equal to 50. And on the second line, we know that V2 over I2, the ratio of the voltage waves to the current waves, is equal to 75 ohms. So let's naively sort of put a wave coming down this way, going in the positive direction, and give it an amplitude of 50. Well, we know that Z1 is equal to V1 over I1 is equal to 50. So if the voltage is 50, the current has to be 1. Well, what happens over on this side? Naively, one might say, okay, well, we know that Z2 is equal to V2 over I2 is equal to 75. The current is just going to keep going, so let's have a wave here with a voltage of 75. And this doesn't make sense at all, because all of a sudden we added half again to the voltage. We just violated conservation of energy, which would be a really good thing, because we could power the whole world on joint transmission lines if this really happened, but it didn't. And it doesn't. Well, then we say, okay, well, let's keep the voltage constant. So we'll have the voltage 50 going in, and we'll cross that out. And we'll say, okay, really what we've got here is V2 is equal to 50. So that means that we've got 50 in the numerator, and what do we need? Something like 0.67 maybe in the denominator, just doing it off the top of my head. Well, this doesn't work either, because now V times I has dropped. We've lost some power by going through there, and there's nothing to lose power here, so that doesn't work either. So how do we resolve this issue? And the way we resolve it is we call this point where the lines just join, and we zoom in on that and call that point Z is equal to 0. If we have a wave of 50 coming down this way, moving in the positive direction, and naively we say, okay, we've got a larger wave of 75 moving that direction, away from the junction. So let's put a 75 on and 50 there. What happens right at this junction here? Well, it would actually make sense if you had a second wave moving in the opposite direction. So we had a wave that summed up positively with the first wave, moving in the negative direction, that had an amplitude of 25. Because then, right at this point, where these two waves add together, you've got a total of 75, which equals the voltage on the other side. It turns out that this also works for current, because you may have one coming in less going this way and some coming back that way. And obviously these aren't 50 and 75 exactly. There's something funny going on here. And now we need to actually go and use some mathematics to figure this out, which actually ends up being pretty straightforward and pretty simple. So we can write our two waves as a voltage wave with positive and negative components, and a current wave also with positive and negative components, where we've just used our definition of impedance, V naught divided by Z naught, for the negative and positive going currents respectively. So let's go ahead and take a look and see what happens at this point in time. Again, let's look in right here at Z equals 0. And we'll define this point to be Z equals 0 because it turns out that in physics, valid physical laws are still valid even if you move the origin. If you move the coordinate axis, physical laws don't change if they're real physical laws. And that says we're allowed to move the coordinate axis wherever we want to. Well, this simplifies these equations of these positive and going waves really immensely because e to the anything becomes 1, and we can just basically cross those terms out of the equation right here. And so now we can actually say if we've got basically on this side, right at the junction V2 and I2, we know over on this side we have V1 in the positive direction plus V1 in the negative direction. The currents over here are going to be I1 in the positive going direction minus I1 in the negative going direction. That minus sign is there because currents have direction. This current we define to be going back in the opposite direction. We also know that essentially this ratio is equal to Z2, just as the ratio here of V1 plus to I1 plus, and this also applies, is equal to Z1. This will also apply to the minus currents. Well, this ends up being pretty straightforward because it turns out that we can then set the following relations. We can say V1 plus V1 minus is equal to V2. We can take this ratio of I1 plus minus I1 minus and set that equal to I2. And let's go ahead and get rid of this 2 because this looks like V squared, and that's not very accurate, is it? Let's make that V2. We know these ratios are equal to Z2. We know this ratio is equal to Z1. We can go ahead and substitute these i's with these types of relations right here. And when you do that, you end up with the following expression. And we're not going to go through the algebra here. But you end up with the ratio between V in the minus direction divided by V in the plus direction being equal to the difference in the impedances. And we give this term, this is capital Greek letter rho, we call that the reflection coefficient. And it turns out that this equation essentially will always tell you the amplitude of the wave that goes back in the other direction. So let's take a look at that. It turns out in this case that Z2 is equal to 75, Z1 is equal to 50. On the bottom we would have Z2 equals 75 and 50, so our reflection coefficient is going to be 25 divided by 125, which is going to be essentially 0.2. So the wave going back is positive and it goes back 0.2. Let's look at another case here. Let's say now we move this transmission line to have 75 ohm impedance and this to have 50 ohm impedance. What happens in this case? Well, we know we've got our wave coming in, and we know its amplitude is going to be 75. We know it's going to be smaller here, maybe something on the order of 50. How do we deal with this case? Well, that's pretty obvious, because essentially what we've got is we need to have a wave of amplitude minus 25. Well, you can't have a wave with a negative amplitude, but you can have a wave that's 180 degrees out of phase, that's shifted and is in the opposite direction. So you've got peaks aligning with troughs. And in that case, the same thing works. What do we expect for the reflection coefficient in this case? Well, in this case, Z2 is equal to 50 minus 75. We divide that by 50 plus 75. And this, when you do the math, ends up being negative 0.2 and it turns out the wave is flipped upside down. So it doesn't matter if one comes before the other. We can certainly have negative reflection coefficient. It just means that we have a 180-degree phase shift. In the most general case, what we generally talk about is some kind of transmission line with a characteristic impedance Z0 and phase velocity being terminated in a load. And this load has any type of impedance. It can be 0, it can be 1, it can be infinity, it can be a complex number, it can be an imaginary number. We'll talk about that in a minute. But what this diagram here represents is a transmission line with some kind of wave propagating down it, feeding energy into the load which you're driving. And that load could be an antenna, it could be something else, it could be some kind of detector, but this is really what we're trying to do with transmission lines, is we're trying to use high frequencies to drive some kinds of loads. We know in this case we just write our reflection coefficient as the load minus the line impedance divided by the load plus the line impedance. And it turns out there are several specific cases that we can look at for this. When the load impedance is equal to the line impedance, the numerator becomes 0, the reflection coefficient becomes 0, and no energy is sent back. This is called impedance matching. And this really is a very important term when we talk about transmission lines, because impedance matching, if you set the load impedance equal to the line impedance, all your energy, all your signal is going to go into the load. You're not going to lose any to reflection. If in the case we basically take this load and get rid of it, and in other words, what we're going to do here, let's get rid of that line, is we're going to replace this with a short circuit. If I can get my pen back here, let's replace that load with a short circuit and do that. In that case, the load impedance is 0, the reflection coefficient is -1, and all the wave goes back 100 degrees, 80 degrees out of phase. If, on the other hand, we basically erase that and get rid of our load, and we basically leave this as an open circuit, so we just get rid of that and terminate it with nothing, the load impedance goes to infinity. If we have an infinity in the denominator and an infinity in the numerator, we know the reflection coefficient becomes 1. Again, all the wave goes back. It also turns out if you put a capacitor or inductor to terminate the line, that's a purely imaginary, or what we call reactive component, that Z load, being imaginary, is going to give an imaginary reflection coefficient, but that magnitude of the reflection coefficient will be 1. All it's going to do is send the wave back with a phase change. And in the most general case, if you have a complex load, a resistor and a capacitor, say in series or something like that, the reflection coefficient itself is complex. And those are reflection coefficients. This is a really important parameter, and we're going to see how that in the next couple of slides leads to something called standing waves on the line, and also then how we can very soon deal with complete circuits made out of transmission lines.